Let's explore the relationship between electric field lines and equipotential lines, or equipotential surfaces. We've seen how electric field plots, such as one shown here, with these red lines that are shown here, are helpful in visualizing the electric fields. In a similar way, these green lines that you see, which are called equipotential lines, are helpful in visualizing constant electric potential. To help get this idea across, I'll first discuss something that is similar, which we find in topographical maps. Here is a topographical map that shows lines of constant elevation. So as you walk along here, for example, you'll see this is all constant elevation. Or here's another visual, and you're walking along this contour line, and your elevation is remaining constant, and hence your potential energy is remaining constant. So as you walk along the contour lines, your potential energy is not changing, and hence no work is done by the gravitational field. So equipotential lines are very similar to these contour lines on topographical maps. So suppose that you want to move a charge in a direction so that the electric potential remains constant. So if I were to take this point P and keep this at 1 volt and move this around here so that it always remains at around 1 volt, and you would find that as I move around, I would have to go in a perfect circle. If I move closer, the potential increases. If I move further away, then the potential decreases. So here now I have a three-dimensional plot of the electric potential of this source charge Q2. You can think of this line along here, this region between the yellow and the green, as a contour line, and here's another contour line, and here's another contour line. But in this case, this would represent constant electric potential, so we would call this equipotential lines or equipotential surfaces. So if I were to move point P so that it would maintain the same electric potential, so here it is at 1 volt, and again here, and you'll see that it's always maintaining this elevation along this contour here. And if I were to move down the slope, I would have to move directly away from the charge. And remember, the electric field lines are moving directly away from this charge, so as you go in the direction of the electric field lines, the electric potential drops. Below are some electric field and equipotential plots that you should know. So here's a single positive charge, an electric dipole, and then two equal positive charges. These green concentric circles represent the equipotential lines for a single positive charge. You'll notice in electric potential plots a couple things. One, equipotential lines do not have any arrows on them like the electric field lines that are away from a positive and towards a negative. But equipotential lines have no lines because they're scalar quantities, so you do not put arrows on these equipotential lines. Secondly, just like as electric field lines get stronger as you get the field lines getting closer, the equipotential lines, as they get closer, there are stronger electric fields. Thirdly, the electric field lines always point in the direction of the maximum potential decrease. So the electric potential will drop. As you can see, it goes from 70 volts to 50 volts to 30 volts in the direction of the electric field lines. Fourth, that you'll see that the electric field lines are always meeting the equipotential lines at an angle that is 90 degrees. Also, you'll note that I've drawn these equipotential lines at constant differences of 20 volts and 20 volts here. So you can draw an infinite amount of equipotential lines, but we customarily draw them separated by the same amount of volts. So as you get further away from this positive charge, the equipotential lines space out to larger degree because you know that the potential is going to drop off even more as you get further away. Now, positive charged equipotential plots are often shown like this. Sometimes we show them with equipotential surfaces because that's in reality what is happening. Or maybe sometimes you will see a three-dimensional equipotential plot that's shown over here. Looks like an elevation map. And here's an equipotential plot for a dipole, and you can see the positive charge is like the top of this mountain, and the negative charge is like a sinkhole. And this is an electric potential plot of a chest of a human. And lastly, in uniform electric field lines, if you recall, these green arrows here represent the electric field lines. Notice they're all equally spaced between the lines and they're all parallel to one another. Well, since these are all equally spaced and parallel, and equal potential lines must be perpendicular to the field lines, then the equal potential lines or equal potential surfaces are also equally spaced and parallel to one another. So as a charge moves from a higher potential, say here at position 1, to a lower potential, it will be moving in the direction of the electric field. You can see it's dropping from 3 volts to 2 volts to 1 volt to 0 volt to negative 1 volts here, and the electric potential is decreasing as you move in the direction of the electric field. So imagine you have a positive test charge here right at this location. If you were to move right along the equal potential line to say position 2 or position 3, you wouldn't be changing your potential. So in essence, you wouldn't be doing any work against the electric field. So no work would be done if you move along the equal potential line. And if you move, say, from position 1 to, say, position 4 here, you would definitely be doing work, and it would be a loss of electric potential energy or a loss of electric potential. And furthermore, the path that you would take to get to number 4 could be crooked and bent. It really wouldn't matter if you did a straight line path or you went along this crooked path. It would still be the same amount of work done, because remember, electric fields are just like gravitational fields are conservative, and so it really doesn't matter what path that you take. So the work done is path independent. So as you move this charge here through this little weird path over here to B, you'll still do the same amount of work because potential differences are path independent. Down below you see a graphical representation of the electric potential inside a conductor. We've been showing just equal potential lines, but you can think of these lines as equal potential surfaces. In this particular case, these would be flat planes. And if you were to draw the three-dimensional view of this equal potential plot, it would look like just an inclined plane. And so as you move, say, from a higher potential to a lower potential, you'll be like rolling down this constant inclined hill. Now let's get a quantitative relationship between this electric field strength of these electric field lines and the spacing between these equal potential lines. So imagine I have a test charge, Q, that moves in the direction of the electric field lines a distance of d. There would be a force acting on this charge, the electrostatic force, which is equal to that charge multiplied by the strength of the electric field. As the charge moves from this location to this location, moving a distance d, there would be work done by the electric field. And the work done by the electric field would be equal to the force multiplied by the displacement. And in this case, we'll call the displacement d. And remember, the electric force is equal to Q times the magnitude of the electric field E. And now we have that multiplied by the displacement d. Now, the change in electric potential energy will be equal to that negative work done, because as it moves in the direction of the electric field lines, it will lose electric potential or electric potential energy. So this is really equal to negative Q times E times D. Now, if you recall, our definition for electric potential was the amount of electric potential energy per unit charge, or the electric potential difference, or voltage, is equal to the change in electric potential energy divided by the charge that was moving. So let's substitute in here. We have negative Q E D divided by Q, and you can see that the charge Q cancels out, and we get that potential difference as it moves from here, the 2 volt line, to say the 0 volt line, would be equal to the same as taking the electric field and multiplying by the displacement. And there's a negative in here. The reason for the negative sign is that because as you move in the direction that of the electric field, the electric potential will decrease. And on the AP formula sheet, this is often written as E average equals negative V divided by D. I personally don't like the fact that they put V. I really think that they should be putting delta V, But this should not be thought as the potential at this location, but really the change in potential as it moves this distance. So this is really a delta V, and this is the displacement as it goes from here to here. So just as a quick example, let's say that this is a parallel plate capacitor, and that this plate is attached to 4 volts, and then over here this is attached to, say, -1 volt. And so the potential drop between these two plates would be a potential drop of, say, 5 volts, because you would drop a total difference of -1 minus 5. So that would be a -5 volt difference. And let's say that the distance between these two plates is, we'll just say, is 5 millimeters. That's the distance between this plate and this plate. We could calculate the electric field of this configuration, this uniform field, by taking the voltage divided by the displacement. So that would be, and that would be negative of that. So negative of -5 volts divided by 5 millimeters, which will convert to meters. So 5 to the power of -3 meters. And this would give you an electric field strength of 1,000 volts per meter. And 1,000 volts per meter is the same as 1,000 newtons per coulomb. A volt per meter is actually the same units as a newton per coulomb. Think of a volt. A volt is really a joule per coulomb over meter, right? And a joule is equivalent to a newton meter. And now on the bottom we have a coulomb times a meter. The meters cancel out, and so you end up as newtons over coulomb being the same as a volts per meter. So now there's a new definition that you can use to find the electric field strength if you know the voltage and the distance that the charge moves from one plate to another. Now you don't necessarily have to go from one side of the plate to the other plate. You could just go, say, an increment of, say, 2 volts to 1 volt, and then all you need to know is what is this distance from this line to this line in the direction of the electric field. And you should be able to calculate the electric field strength. I should also mention, too, that this electric field is often called the potential gradient or potential slope. What this means is that the electric field is equal to the negative rate of change of the electric potential divided by the displacement that is moved. I'm going to call this delta x. So in a more precise way, this equation should be really written as, say we look at the electric field in the x direction, we would be taking the potential drop along that x-axis divided by the displacement that it moved. Now you could apply this also and try to find the electric field along the y-axis or the z-axis. This means that if you were to plot a graph of, say, potential versus displacement, and you were to get a graph that looks like this, and the points were all moving down a nice linear way, then the slope of that graph, which is the rise, the change in potential over the change in distance, would be really the electric field strength. And it's the negative slope of that. And one last important caution I'd like to say, that this relationship that we just came up with here really only holds for a parallel plate capacitor where you have a uniform electric field. Remember, these field lines are nice, constant in magnitude and direction. So they're all equally spaced and parallel to one another. You can't use this formula in a point charge configuration because the electric field is not constant. So you can only use this formula here for a parallel plate capacitor, a uniform field situation. Okay, you should be now ready to tackle on the next two problems.